Good morning. Today we start a new topic about kernel machines or support vector machines. From previous lecture, we studied the non-parametric and semi-parametric machine learning, and we have discussed several algorithms. Still, we have little bit something that we left about decision trees. And we try to come back to decision trees maybe at the end of this lecture or next week. But today is very important, and one of the most important topics actually in machine learning is the kernel machines or in support vector machines. They have a lot of applications in different areas, and it is preferred over many other algorithms because of many features that we are going to discuss and present today. If we start with the definition that kernelization, what is the meaning of kernel? Actually, kernel is in general, in signal processing, is the pre-processing of data in order to reduce the size. So, and it has also more like specific definition that it is the most selecting the most effective sets of data. They are called kernels, so the nucleus of the data, the most important or the most effective part of data that it can be used to simplify the problem. So if the problem has very large size and for example the number of data is very large, so we just select the most important or the most effective parts of this data to solve the problem. This will reduce a lot of the computation requirements to solve the problem. The word kernel is also used in computer science to define the operating system. The kernel of operating system is the part of that operating system in order to manage and to schedule the resources. We know that in computers we have the processor and memory. So how to manage the resources of the computation resources and the memory in order to handle all the requirements of the computation. For example, for your computer, you have a lot of requirements and how to handle them, how to manage, how to divide the time resources with the memory and also with the processor. This is called the kernel of the operating system. It is known that it is NP problem or non-polynomial complex problem. However, it can be optimized in different ways by looking for the most important or making some priority in order to solve the problem. Okay. Why kernel machines are important? There are several reasons. One reason is that it is linear, or it is, to be more specific, to say it is convex problem. Okay, it is convex. Actually, it is linear, or it can be quadratic in terms of the parameters. So, and for convex optimization, as we have seen in part 1 in this course, that we have only one solution, which means that we can find it easily, relatively easily, compared with the other non-convex problems. And also, we have very efficient packages to solve such kind of linear optimization problems or convex optimization problems. The second thing that the support vector machines, the solution or the optimum solution is directly related to the data itself. So it is somehow easy to make some interpretation about the data, because you can see that the data itself, you will see that the impact of data over the algorithm itself. This will be explained in more details today. And the third one, which is very important, that you don't need to use all available data. We need only the support vectors. Sometimes you have, let's say, you have database with like millions of inputs. So you have dimensions like the dimensions D. For example, we have this attributes, which could be explained like from x1 to xd, x1, x2. So this is the dimension of the data, the attributes or the features. If it is, for example, related to health, as we see before, that can be the age, the gender, the some parameters of health parameters like the sugar in the blood or whatever. So we have D features, and we have then, this is the data itself. So the data, we have N data. So N can be like 10,000, can be hundreds of thousands, can be millions. But in support vector machine, we can see that if we like to make like classification of this data, we need only the support vectors. The support vectors can be very few numbers of those N. And the support vectors, as we will see today, we can design them to be not related to the dimension D. It is related to this the numbers of N. And in many times, for example, we can, just an example, we might have only 3 support vectors. For example, 3 support vectors. What it means? It means that you design your boundary or the classification or the discriminant function based on only 3 support vectors, only 3 of this N. N can be, as I said, millions. It can be 3, it can be 4, it can be 10. Sometimes, of course, can be higher numbers. But we don't need all of them. And it is not related, the complexity is not related to the dimension D, because the dimension D can be also very large. Can be very large. Like in image, for example, if you would like to build some face recognition, the image can be millions of pixels. Okay? And we have like 50 or 60 maybe samples. So we are not interested to build algorithm which is like the complexity is related to the dimension D, and it is related to only to the number N, but not all N, only support vectors. We can use in order to build the discriminant function. Now today we talk mainly about the classification. We talk mainly about the classification process using the support vector machines. Okay. Of course, there is one thing more here. If you remember from part 4, when we talk about parametric classification, one of the methods that we divide, for example, if we have this as a classes, if we assume that we have only 2 classes like C1 and C2, okay, we were collecting the data in each class, C1 and data in C2, and then we estimated the parameters of the data by starting with assumption. For example, we started, if you remember, we started with the assumption that the data in each class is multivariate normal distribution. If you remember, multivariate normal distribution. What we need for multivariate normal distribution, we need to estimate the mean and the covariance matrix. So, and then we used maximum likelihood in order to estimate the mean of each class and the maximum and the covariance matrix of each class. And based on that, we built the log likelihood function, if you remember. And then after that, we decided that this is for the discriminant function. If we have a new input, then we just projected to that discriminant function and selected the higher one. Is it J1 or J2? If you remember from the parametric optimization or parametric classification that covered in part 4. Here, things are much easier. Here we don't need to think about the parameters. We don't think we don't need to think about what kind of distribution or about the statistical behavior of the data. We ignore everything. What we are interested here we are only interested on the boundary between data. So whatever the distribution of the data, I don't care. But this data that I have already in the database, then I am looking to find the optimum separation between two classes. This is what we are looking for, and we don't care about what kind of distribution that each data they have. Okay, so in that sense, it is much easier than the others. So the idea here that no need to solve like easier problem by solving harder problem, because if we are looking to find the parameters, the first problem that we started by making some assumption that the distribution is multi-normal or multivariate normal distribution, which actually it can also solve source of biasing if the data is not multivariate normal. And then we start to estimate the parameters, and there is error in the estimation. And after that, the problem has been like solved in more complex form. However, in the support vector machine, as we will see, that it can be solved in much easier way. Okay. Since the support vector machine is basically a linear function, so it is linear in parameters, as you can see. It is linear in the parameters. Of course, we can extend this by looking for higher dimension of the data, but still it will be linear in parameters. So this is one of the main features of the support vector machine, that they are convex problem. So convex means that it can be linear or quadratic form of the or shape. So in that case, we have the discriminant function is given like that. So the discriminant function of data x is bold x is just vector of the parameters. So it is x1, x2 until xd. Okay, so here it is transposed. It is like column vector. This is if for one element, but of course we have here we have here n by d. We have n rows and we have d columns. Okay, so the idea here that our discriminant function of x given wi and wi0 is given by this. So this is the offset, and we have this is the projection of x over this linear function. So this linear weight is wi is also a vector, column vector, with like w1, w2 until wd. Okay, so our idea is how to find the optimum w in order to correctly classify the data. Of course, here we are talking about supervised learning. We have already labels. Here another form that is quadratic. So it is quadratic discriminant function, but we will talk mainly about the linear one, not the quadratic one, because the quadratic one can be generalized when we talk about the kernel tricks by the end of this lecture. Okay, this is just like introduction. So here you can see that instead of multiplying the weight by w, but by x, we can multiply it by phi of x. And this phi of x is called basis function. And in that sense, we can also solve for non-linear classification with linear equations. So it is still linear in parameters, as you can see. It is just weight, the same weight vector, but instead of multiplying weight vector in x, now we multiply it in some form function of x itself. And in that sense, it is still linear, but it can solve also non-linear functions. One example here, if you have two inputs like x1 and x2, you can now define your phi that like x1, x2, x1 squared, x2 squared, and x1 times x2. In that sense, now you have like vector z. So we have z, z1, z2 until z5, and now we solve what? We solve the problem that ji of z now, not of x anymore, that equal to w transpose times z. So still the problem is still linear. The problem is still linear, but the data itself, because we had here like x1 and x2, x1 and x2 in our data. Now you need to extend it more. So we have x1 and x2 and x1 squared, x2 squared, and x1 times x2. So we have larger like dimensions, large number of dimensions, but the problem itself is still linear. Still linear. And this is also one of the most powerful features of the support vector machines or the kernel machines. It can solve highly nonlinear problems using linear operation, and this feature actually gives it some like it is preferred over some other algorithms, like over neural networks, for example. It is preferred to solve some problems over neural networks. Of course, it is not as strong as neural networks to resolve very highly and hidden nonlinearities, but still it is powerful enough to solve many practical problems. This is a visual explanation how it works for this trick, that to convert to solve nonlinear problem with linear operation. So now if you have this one-dimensional data, so we have only x here, and we have two classes. A class is circle and the class is a star, as you can see them. So now if I asked you to find linear classification for this problem, there is no linear classification actually for this problem. For the one-dimensional problem, we don't have linear classification, because to classify this, you need to have circle here, and this is not linear anymore. But if you extend the problem to be like x and x squared, so we increase the dimension now. It was one dimension, but now we have two dimensions, x and x squared, and now the problem becomes in nice shape that you can easily have a linear separation for the problem. So this is the same concept will be applied also for much more complicated problems and higher dimensions. Okay. Geometry of the linear discriminant function. So we have here like class 1 data, and we have class 2 data, and then we are interested to find the optimum discriminant function, that we say that anyone or any element belongs to C1. If you apply them to this function, the result will be positive. And if you apply anyone from the class 2 to this function, the result will be negative. So in that sense, that J1 of x and J2 of x, that in order that if the data belongs to class 1, J1 of x will be greater than J2 of x, and if the data belongs to class 2, J2 of x will be greater than J1 of x. In other words, if we take that J1 of x J of x equal to J1 minus J2, then C1 makes J of x greater than 0, and C2 makes J of x less than 0. So this is basically the concept here that we are looking to apply. Okay, now we like to apply this for any dimensional data. So we have x here, wi transpose. This is the weight. Now our problem is to find the optimum weight. What is the optimum weight for certain data? Now you have data, and you are looking for the optimum weight in order to separate between C1 and C2. Let us start with the assumption that the data is linearly separable. So the data itself is already separable, it can be separated in linear dimension. So now our idea is to find the optimum weight, W vector and Wi0, the offset, in order to separate both classes in good way. Okay, so Ji of x, given the parameters of the linear discriminant function, is equal to ai, where ai should be greater than 0 if x belongs to ci, to class ci, and should be less than or equal to 0 if x does not belongs to the same class ci. This is generally for any number of classes. You can see here that how linear separation works. So, for example, for this class, for the class C2, we have this linear discriminant function. So for any element is in C2 will be positive, and any other element above this will be negative. And also this is for the class C3, and this is for the class C1. So we need here 3 discriminant functions in order to classify each class. Okay. However, of course, it is not easy to find, or in the practice, actually, it is very rare to find like nice linearly separable data like this one. So we don't have anything here, we don't have anything here. So usually it is not practical. Okay, so it is maybe ideally linearly separable, but it is in the practice it doesn't work in this way. And even in the practice, even if we have certain data that they are ideally separable, but because of noise, because of biasing, that cannot be in this way. So this is more like realistic. So we have the data is yeah, it still can be separated, but we have errors. So here we need to take into account how to find the optimum linear discriminant function in order to minimize those errors, and maximize the separation effectively. Okay, how to do that in math? Usually when as we have seen here, that ji of x equal to wit transpose times x plus wi0, the distance between the point x and the border, the distance between the point, any point x and the border line ji, defined by ji, is equal to ji divided by the magnitude value of the weight. The magnitude, this is known from linear algebra, that the distance between the input x and the hyperplane, the minimum distance, actually not the distance, the minimum distance, is given by the absolute value of the function or the discriminant function at the point x divided by the magnitude of the weight vector w. Okay, and now to explain this, let me show what we are doing here. Assume that we have some data, and maybe we have, yeah, assume this is the linear separation between two like classes. So we have one class here, and we have some other class here. Let me put it a little bit halfway. Okay. So we have here class 1 and we have here class 2. Okay. And this is ji x. Okay. ji, or it is j of x because only 2 classes. And this is the line that jx equal to 0. Okay. Of course, if we call this is like, for example, PE, then because if it is here, so it will be like W, or this is W, Wi0, okay, or W0. This is the shift. The W0 here, it just add or subtract some shift about the line, and for the weight, for the weight W is makes the like the slope of this one. So the slope, it can be controlled by W, and the distance can be controlled by the offset W0. Okay, it is W0. Yes. Of course, when we design this, we can make them what is the optimum W, which makes that for class 1 to be greater than or equal to 0, and for class 2 to be less than or equal to 0. But what happens if we make that? Then we will have something here, and we have also something here. Okay? And because of any noise or disturbance, this can be misclassified to this direction, and this can be misclassified to this direction. Okay. Then how to avoid this problem? We can avoid this problem by making some margin. So here we can add margin to say that I don't want to see anyone from class 2 crossing those margins. And here we define this margin as the distance 1. 1, and here also 1. Okay. This is the reason that we put here greater than or equal to +1 for the class 1, and this should be less than or equal to -1 for the class 2. So now we have some margin, not only the boundary, but we added also some margin that we don't like to see the data or the elements here to cross this margin. So this is called hard margin, like the discriminant function. It is hard margin, so I don't want to see anyone that crossing this margin. Okay. And you can see that the Wt times xt plus W0 to be greater than or equal to +1, not 0. Greater than or equal to +1, it is like margin for the class 1, and less than or equal to -1 for class 2. Class 1 means that the data or the response is equal to +1, and for class 2, C2 when RT equal to -1. Remember, this is, I just remind you that it is a supervised learning. So we have already the classes, we have the labels of the data. Okay? Now, if you multiply RT by this function, so this one is greater than +1. If it is multiplied by +1, it will be still greater than or equal to +1. This one is less than or equal to -1. If you multiply it by -1, it will be also greater than or equal to +1. So in general, we can, instead of using two equations, we can rewrite them in one equation, that RT of Wt xt plus W0 to be greater than or equal to +1. So if R equal to -1, then we achieve the second equation. If R equal to +1, then we achieve the first equation. So this function is valid for both classes. This is what we are looking to solve. Okay. Now the distance, as I said, the distance between each point and the border, this point, and also between this one and the discriminant function, the distance is given by this equation. It is the j of x is given by this function divided by the magnitude of the weight. This is basic from linear algebra, that we know that the distance, the minimum distance, is given by this equation. Okay. What is our aim? Our aim is to find the weight W in order to maximize the distance. So, because after the projection, I like to keep the two classes as far away from each other as possible. So this is our aim, is to keep the distance between entries or instances of each class to be as far away as possible from each other. So what is our aim? Our aim is to maximize this, to maximize the distance. Okay. However, the weight, the magnitude of the weight, you can have very small weight here. If you have very small weight, then the value will be large, but it will be fake, because it will be small for every entry in that case, in that sense. So what we can do, what we said here, that the distance should be greater than or equal to some factor rho. And if you multiply them together, then the magnitude of W times rho, this the magnitude that it is easy to fix the value, because, for example, just to explain this, if you have two-dimensional problem, then W transpose x equal to what? Plus W0 equal to W1 x1 plus W2 x2 plus W0. Okay. What is the magnitude value of W? Magnitude value of W equal to square root of W1 squared plus W2 squared. Okay. Now, if you multiply it here, all the function, you multiply it by 0.0001, for example. It will be multiplied in both of them. Then this magnitude value of W can be very, very small. However, you didn't increase the distance actually, because you multiplied this small value in every element here. So what you did will not increase the distance, because the distance will be increased, but relatively it will be the same, relatively between each element. So how to solve this? We make this value as a fixed, for example, equal to 1. So we fix this as some number, for example, equal to 1. And our aim is what to do? We like to maximize row. We like to maximize this row. Maximizing row now, in order to get the same fixed number 1, means minimizing the magnitude value of W. So minimizing W here, minimizing W, will maximize the distance between each element and the border line. And this is what we have done as in form of optimization problem. So now we minimize the weight W square. We take square, of course you can take it without square, but we take square to make it a smooth function. Subject to, without square, but of course you need to have the norm, because this should be the norm of the weight. Subject to this one, because this is what we need to achieve, that the distance between each entry, each class should be greater than or equal to a +1 from the border line. If we solve this problem and find the optimum weight, then we have solved the separation problem. Okay, let us see how to do it. If you remember from part 1, when we talked about Lagrange multiplier, now we have optimization with constraint, and if you remember that we have the unconstrained version of this problem. So I will try to explain it here. So now we have the primary form of the optimization. We put the first that we like to minimize. It is half the magnitude value of square of W, which is nothing but W transpose times W. Okay, and the subject is plus. What we do here we have the constraint. We add the constraint and we multiply it with the Lagrange multiplier. If you remember, or if you revise it, lecture 1, when we talk about this, so the Lagrange multiplier, it is alpha multiplied by this one. So it is RT. Now, in data, let me here have this kind of data. So we have X, and then we have the response R. Okay, so we have X1 until XD, and we have the response R. Response R is the class, so it is +1 means C1, or -1 means class 2, class 1, and so on. Okay, so what we should do here, we take every element in the data, so it becomes like alpha 1. This is the first Lagrange multiplier, multiplied with what? Multiplied by the equation. This is R1, the first element in your data, multiplied by W transpose times X what? X1. X1 is the first row in your data. I am trying to do it like step by step, just to understand what I'm doing. But in the implementation, of course, it will be computer programming. So no one solves it by hand, but at least you understand how it works. So it is plus W0. Okay? And here it should be greater than or equal to +1. We take the +1 in the other side, so it becomes like -1. This is the first element. Plus the second row, it will be alpha 2 times R2 times W transpose X2 plus W0 -1 plus alpha 3 times, and the same until we reach to the last element in the data. It is alpha n times Rn W transpose Xn plus W0 -1. Okay. Now we have added all parameters or all elements of in your database in the primary form of the function. So of course, instead of doing it in this way, we put it as a summation, as you can see. Yes. So we put it as a summation. So it is half lambda w magnitude square minus summation alpha t. Alpha t is the Lagrange multiplier times the constraints. Okay. Of course, you can also expand this one, and you have this as separated element. Now, to solve this function, we differentiate the primary form with respect to the weight in order to find the optimum weight. And when you differentiate the equation and equal to 0, then you got the optimum weight. So the optimum weight is the summation of alpha t times rt times xt. Of course, t is the element, as I said, from 1 up to n. Okay, and the second differentiation with respect to w0 is equal to 0, and this gives us as a requirement that the summation of alpha t times rt should be or must be 0 in order to achieve the maximization or the optimization problem. Okay, what is missing here? This is the optimum weight, but here we don't know actually the Lagrange multiplier values. The Lagrange multiplier values is unknown. Okay. And if you remember also from the first lecture or the first part when we talk about Lagrange multiplier, we said here that the Lagrange must be greater than 0 in order to have like solution. So if alpha t is less than 0, we put it equal to 0. And if alpha t equal to 0, then it will not have effect. Okay. So which one will contribute in W, as we will see soon, is the support vectors. What means the support vectors? Let me explain before I go to math on this figure. Now, this is the data that we have already. Okay, so in this data that we have, you can see that all these elements, maybe we have millions of them, but they have no effect because they are already in the right direction. They are already in the right side, and they are far away from the optimum discriminant function. They are far away, so they have no effect. They will not they will not make any effect on the shape of this discriminant function. Also for these elements which are far away. Okay. Now assume that we have one here, maybe we have one of them maybe here, and we have also one here. You know, now these two, those are the only support vectors. They will control the shape of this discriminant function. Only two vectors. Only this x, maybe this is, for example, x number 30 in your data, and maybe this is x number maybe 45 in your data. So only two vectors in your data might like control the shape of this discriminant function. All the others are not. So in that sense, these two are called support vectors. They call support vectors because those two which will like formulate or make the shape of this discriminant function. The others are not. The others are not included at all. So sometimes you have millions of data and end up with a few vectors, a few support vectors that you can solve. So this is actually the main feature of this support vector meshes. And if we need, of course, and we need to solve for the Lagrange multiplier, because here the Lagrange multiplier is important to find in order to solve this one. And to solve them, then we go to the dual form of this function. The dual form of this function simply by substituting w in this w in the previous equation in this LB, and then we got the dual form. So the dual form that we maximize with respect to the Lagrange multiplier, as you can see. So we maximize with the Lagrange multiplier, and we have this as a constraint. This is called the quadratic optimization problem, and there are many efficient algorithms already in Octave or Python or whatever package or programming package that you use, that you can find ready functions to solve this one, and they are very easy to solve, and also the complexity is not very hard. So the upper bound of the time complexity is in order of n cube, and in order to find all parameters or all Lagrangian factors. Once we found all Lagrangian factors, okay, then we know which one of our data are the support vectors. Okay, now you give me like CD with database with like millions of data, and I make this operation, and then I find the support vectors. I found, for example, there are like, let's say, 100 support vector in your data. Then I build this W. We built this W and W0. Once they are built, then we got learn the data. So I give you like a nice function, just one function, then you can use it in your applications directly. You don't need to do it again. This process is done once over your data. Once you did it, so you have solved the problem. You got the machine learning to learn from the data what is the optimal separation of your data, and then you can apply them for future or for prediction or for estimation and so on. So those are the support vectors. The support vectors are the vectors which are achieving that the Lagrange multiplier is greater than 0. Once we found the optimum weight, okay, and we know that on the border the optimum vectors must be 1, and or support vectors must be 1 on the border, and in that sense we can also calculate W0. So you can substitute any of your data, or you can substitute all your support vectors and calculate the mean of the W0 of the offset. So this is the support vector machines. However, there is only one problem with this hard discriminant function, that in many problems, even they are linear separable, but actually they are not nice in this way, that the data is, you have this all this margin, the margin here equal to 2, as you can see, the margin equal to 2, because 2 actually 2 divided by the magnitude value of W, because this is the distance. So the margin is equal to 2 between the two classes, because one class is 1 up to the border, and the other class is 1 up to the border. So the total distance is 2 over the magnitude value of W. But in many applications, what happens if the nature of your data, you have something here. You have something here. So even whatever you use any vector of W, you will not be able to get rid of those elements. How can you solve this? In that case, we need to use what is known as soft support vector equations, or soft discriminant function. And this can be done easily by simple modification of our first equation. Okay, we take a break for 15 minutes, and after that we see how to solve the soft discriminant function. Okay, hello again. So now we continue in the case that hard margin is not working, because the data itself cannot be projected in the way that to have this 2 over magnitude value of W to be free of any of them. That in that sense, we need to relax this requirement. Relaxing the requirement, we define a slack or relaxing variable is like T of T to be greater than or equal to 0, and we add it here. So now we are not requiring that must be greater than or equal to 1. Of course, it is nice to have it, but in case that we don't have it, then also we can relax this requirement by subtracting this T for every data element T, or every instance T. Okay, so this one is greater than or equal to 0, which means that if it is 0, then we have the same as before, the same problem as before. So this area is empty of any of the instances. But if t of t is greater than 0, for example, if it is 0.5, then what happens if it is 0.5? Then we might have data in between. So we have data in margin. Okay, if it's equal to 0, then we have data on margin. But if it is greater than 0, then we have data inside the margin until 1. So this is greater than 0 and less than 1, then we have data inside the margin. If it's C of t, or C of element t was greater than 1, what happened? It means that this data maybe just jump to the other side. So it is called misclassification. Now we have misclassification of the data, or misclassified the data because of that. Of course, misclassification can be happen due to noise, due to biasing, or other problems as well. Or because maybe the problem itself is not linearly separable, so we have some nonlinearities inside the data. We have some nonlinearities makes the data to be dropped to the other side as well. Yes. So what is our problem now? Or how can we define the problem now? It can be defined in a nice way, in the similar way as we did before, but we define the soft error. What is the soft error? Is the summation of this at t for every data element t, from t equal to 1 up to n. So the summation of these errors, it will be like total error when we solve the optimization. So what we did here, we added this total error to the minimization problem. And we multiplied by this factor c, and this factor c is called penalty factor. This is the penalty factor c. So now we added it to the summation. Of course, c we can select, or we can like specify them as a compromise between minimization of the or maximization of the distance between elements, and also minimizing the errors. So this is the penalty part of crossing the margin. And then we have the same like constraint. So the discriminant function should be greater than or equal to 1, but minus t at t. And of course, t should be or must be greater than or equal to 0. Now we solve this again by using Lagrange multiplier, as we did before. So we have the primary form of the Lagrange multiplier is the first element, this one, plus c, plus the error, soft error part, the penalty part, and then minus Lagrange multiplier, alpha t, multiplied by this. Of course, we take this to the other side, so it becomes minus 1 and plus t at t, and also minus and to guarantee that this to be greater than or equal to 0, we multiply also with the Lagrange multiplier mu for every data entry t. Now we differentiate this with respect to w, and with respect to c, and also with respect to w0 as well. And now after solving this, we have the primary form. So the optimum weight is just as before, exactly as before. And also the requirement, the summation of alpha t multiplied by the response t should be 0, is the same as in the case of hard margin support vector machine. And the third differentiation now with respect to t, it gives us that this requirement that t minus alpha t minus mu t must be 0. And solving this, and we know that alpha t, it should be between 0 and c. By solving this one, it's between 0 and c. So this is the new, actually, the new requirement added after introducing this relaxing parameter. After introducing this relaxing parameter, the slack parameter or slack variable, the new thing which added to the requirement is that alpha t, before we want this Lagrange multiplier to be just greater than 0. Now should be greater than 0 but less than the penalty factor C. Okay. We substitute in the primary equation to obtain the dual form, where we convert the problem from d dimension to only to the n dimension, and now we have this is the new optimization problem that we need to solve for the Lagrange multiplier. So now we have this problem and we solve it for the Lagrange multiplier in order to find the Lagrange values, and the Lagrange multiplier values should be greater than 0 and less than or equal to C. Okay, and the optimum weight again is the same. So those are the support vectors. Support vectors is the vectors where we have alpha is not 0. Alpha is not 0, is greater than 0 and also less than C. So the maximum of alpha now is C. Yeah. Let us look to this general shape of the discriminant function. Now, if you look to A is the instances that are correct in the correct side and far away from the margin, like this one A, and also on the other side we have in the class 2 we have this is A. So those will not affect the selection of the margin. Okay, so those are not support vectors. Then we have the elements on the margin. So the element on the margin is B. So this element, this element, this element, also this element. So those are B's, that the elements or the instances on the margin. Okay, and then we have the elements in the margin. So they cross the margin. Those, for example, but they are still in the correct side. So we have C, those the element on the in the margin C, and also this one is C, and C, this one. So those are the elements in the margin, but still in the correct side. And finally, we have D is the elements which are like misclassified. So those, for example, D, you can see that this element is belongs to class 2, but it went to the other class, to the other side, and also this element D, so they are misclassified in the other elements. And actually for every A and B and C you can see what will be the result. For example, for those who are non-support vectors, those like A, we have already that RT times the discriminant function is greater than 0, and C equal to 0 and alpha T equal to 0 for those elements. So they will not affect anymore the discriminant function. And B are the instances that are on the correct side but on the margin. This is B. And for those elements, we have a T equal to 0, but we have the Lagrange multiplier less than C. C is the penalty factor. And for those who are in C element, so they are in the correct side, but they are in the margin. And for those, we have a T is greater than 0, not 0, but also we have the Lagrange multiplier equal to C. And finally, for the misclassified data or the wrong data, we will have a T greater than 1. And also we have the Lagrange multiplier values equal to C. You can see that every element here is support vectors except A. Those who are here in the right side but far away, and those who are here which is the right side but far away from the margin, they are not support vectors, and we don't need them in order to solve the problem. We don't need them in order to solve the problem. The upper bound of the error by using the support vector machine is less than or equal to the number of support vector divided by the total number of n. So this is just estimation about the upper bound of the error. Okay. So far we talked about linear classification with using support vector machines. Now, what if we have nonlinear equation? How to solve the problem in case that we have we tried with linear, but it didn't work at all. So the errors was very, very large. even with the relaxed version in the soft region support vector machine, didn't work. So the number of errors, E of n, this one, that was very high. The misclassification was very, very high. So it was clear that we cannot apply linear classification anymore. Then we need to use nonlinear classification, but still we like to use the support vector machine with linear parameters in order to solve the problem with a linear form. It is the same as we started today, that we can increase the dimension of the problem in order to have to solve the nonlinearities of the problem. And now instead of using x, we project the problem to higher dimension. So we have z now, which is phi of x. Phi contains several elements, where zj equal to phi hat of j at x. So phi hat means that it is one element, it is a scalar, but this phi is a vector of functions. Now we can have like k elements. So actually we have mapping the d-dimensional x space to the k-dimensional z space. So originally we have d dimensions. For example, if the problem is we have some for bank, and the bank has some customers, and they use some attributes of the customer, like for example the age of the customer and salary and saving money that they have, and own apartment and so on. So they have some information about customers. And then assume that we have, this is x1, x2, x3, x4, and we have x5. Then we have the classes here of each customer. Okay, so we have 5 attributes now. We wanted to make classification between, for example, maybe we have 3 classes of this, and we try with the support vector machine with the linear version. We tried it, but we failed. We failed, but because of the misclassification was very high. We were not able to learn from this data. So the data, we failed to have very good classification of the problem. Then we came to the conclusion that there might be some missing attributes, or can be also the problem is highly nonlinear and cannot be linearized in this shape. So maybe you decided to use, instead of using this x, because now we have x equal to x1, x2, x3, x4, and x5. So the dimension now is 5. But you tried, I will show, of course, there are some kernels, like well-known, functions that it is widely used. But one possibility that you use vector z, like x1, x2, x3, x4, x5, x1, x2 times x2, and x3 squared, and x4 divided by x5. For example, just example. So now you have new dimension z. Still, it is function in the same attributes, but now we have 5, 6, 7, 8. Now we have 8. So z we can say that is z1, z2 until z8. So now our new dimension is 8 elements or 8 attributes, which is deduced from the original attributes. By adding these elements, we might be able to find some nonlinearities, or to classify even nonlinear problems. However, how can we build this? Of course, if, for example, here you know that the age and salary, there is information in age, there is information in salary, but also there is information if you multiply age and salary. If you multiply them together, there are some hidden information can be relieved or released by multiplication. And here, for example, x4 divided by x5, you can find something. I mean, it is a general, and you may have some like justification what to use. However, there are many like ready kernels that can be used for this conversion. We will talk about them later. Yeah. Now the problem becomes like that. So it is W transpose times Z. You might ask, where is W0? Since we convert the problem, so we can simply like make this Z equal to, and we can add 1 here. By adding 1, it is like the offset, or you can add it at the end. So just you know that where you added 1, then it becomes like the offset of the problem. So you don't need to solve it separately for W0. Okay, and now we have J of Z equal to the transpose of the weight vector T, W of T times Z, and we know that Z is phi of X. So the problem itself, it becomes like J of X equal to WT phi of X. Everything else is the same. I mean, how to solve the problem after that, it becomes the same, because now we convert to the linear version. So we can apply the same like either hard margin support vector machine or soft margin support vector machine. Okay. So now it becomes like the problem is the same as before. So we minimize half of the magnitude value of W squared, and this is the penalty for the region, for the margin, for crossing the margin. And except now the constraint now is defined in the new space. Now this is our constraint, that RTWT phi of xt is greater than or equal to 1 minus T at the element T. So this if you want to use X still, but you can also use Z. You can just multiply by Z and forget about X, and now you have a new vector Z and play with Z instead of X. However, it is good to use it here because I want to show something. So the Lagrange multiplier for this problem, again we use the Lagrange, so we use the original cost function here minus the constraint after conversion. So it is multiplied by the summation over every elements in the data. So it is the Lagrange multiplier here, like minus 1 plus T at T, and this is for the positivity of the slack variables, and then we differentiate with respect to W and with respect to T, and then we got the very similar actually to the previous result. This is the optimum weight. So the optimum weight equal to the summation of the Lagrange multiplier multiplied by the responses multiplied by phi of xt. It was xt, but now phi of xt or z. And what is missing from this is the Lagrange multiplier, where we can solve it by substituting back this function in the primary form to get the dual form, and then we have this shape. Okay. Actually, if you look to this equation, this the dual form that we need to maximize with respect to the Lagrange multiplier values. You can see here that we have phi of xt multiplied by phi of xs. Of course, this is over t and s. It means that you take the correlation between x and t and x at s. Here we have the phi. Phi is the conversion of, or for example, as we did here with z. Okay, so this is phi. This is phi of x now. Okay. They said here, if you look to this function, because this will be valid only for those which alpha t are non-zero. If it is 0, of course, it will be 0, so you add nothing here. But once we compute them, and we know the set of Lagrange multiplier, which are not 0, then we know which one of the entities are not 0. And then instead of using this phi transpose times phi, we can use this k. K here is called kernel function. It's called kernel function. The kernel function between xt and xs. There are already some kernel functions already that we can use. For example, if you are using Python, you can select what kernel function that you like to use. The good thing here that, for example, in biotechnology or in bioinformatics, you have a lot of data related to certain cell or related to certain disease, for example, and then we found which alpha T is not zero based on the data, and then we found also the best kernel which can classify the problem. For example, if this medicine cause these problems, or what kind of problem classes that this medicine can cause, for example. And once we found all the parameters which are non-zero, because for 0 and less than 0, this is 0. It is not useful anymore. But for those values which are greater than 0, and of course this is then equal to the penalty C, so we found all of them. And once we found those support vectors, then we can build this kernel function. So once we build the kernel function or the kernel parameters K, then we have it ready. So we can send it to any research center, for example, to use it. Because, okay, let us see mathematically how it works. For example, now, you have data, as I said, from for example, from certain medical research center, or from like finance research center, or whatever. And then based on the data, we classify them. We classify the problem like over K classes, can be like K classes. And once we classify the problem, we found the support vectors from the data they have maybe 1 million entry of data. We found those support vectors. Based on the support vectors, we built the kernel function. The kernel function is x and xt. What is xt here? Or xt and x doesn't matter. Doesn't matter. Okay. Xt and x. What is xt? Those are the support vectors that we retrieve them from data after learning. After learning, we end up with this k. This k actually represents all data that we have. Now, if we want to see new data that it was not already in the training set, and now we like to classify this new data. Is it will this cause like disease 1 or disease 2 or disease 3 or disease 4, for example? If this data will cause fault 1 in machine or fault 2 or fault 3 and so on. So what you do, just you have this k, which already we built based on the learning, and then you put the new x. This will give you directly after this 5x, after building this 5x, which is based on this one, this gives you directly which class you will have. Which class you will have. So it can be used for prediction. It can be used for prediction for new entries. And this is actually the aim of our learning here. What is the aim of machine learning? The aim of machine learning that we have a lot of data. We like to get like information, and we learn something that can be used later to predict for the new inputs. So this is the reason that it is called kernel machines. Okay. What kind of kernels that we have? We have, as I said, many like different kernels, but maybe the most three popular ones are called polynomial of degree q, and radial basis functions, and sigmoidal functions. We have also like some tangent functions. We have several actually kind of like kernel machines that can be used. For polynomials functions, that k of xt and x is given by this formula. So it is xt transpose times x. This is xt here means that the entry t plus 1 to the power of a q. So for example, if q is equal to 2 and the dimension of the problem is 2, so if we call them like x1 and x2 and y1 and y2, then you will have this shape. So it will be x1 y1 plus x2 y2 plus 1 all square, and then you will have this one. So our original data x was like x1 x2, but now the kernel function that we have not only x1 but we have x1 y1 x2 y2 and so on. The basis function, if you look to this one, the inner basis function is given by, from this equation, is 1 square root 2 of x1 square root 2 x2 square root 2 x1 x2 and so on. Because if you multiply phi of x time transpose times phi of y, you will receive the same kernel function here. We can have also the radial basis function. It is given by this equation, which is actually measured. The concept behind kernel, that is a measure of similarities. Measure of similarity. Okay, so it is important to remember this. So it is measure of similarity. As the functions are more similar, then the kernel gives you higher number. If it is less similar, then it gives you smaller number. And for example, for this one is always positive, but it can be large or small. So here, if the xt is the same as x, so this will be 0, and this will be the maximum here is 1. Otherwise, it will be, as you are far away from x, then you will be closer to 0. This one is the same as the sigmoidal function, but here for +1 and -1. So it can be +1 if you are in the same direction and the similarity is the same and very high similar. But if they are dissimilar, then it will be also with negative. And if they are uncorrelated, it can be 0. Okay. Yes, this is one just exercise to show how to define them. The good thing with kernels that you can use them. For example, if you have k1 is a kernel function and k2 is another kernel function, then also any scalar multiplication of a kernel is also kernel, and also summation of kernels is also kernel, and dot product of kernels is also kernel. So this is one thing that you can also expand the space of kernels, because sometimes we have data that it needs different kind of kernels to be used, and then we can use combining kernels in some ways in order to optimize the kernel type. So this is just like a proof that the summation of kernel is also gives a kernel. Okay. Yeah. Now actually what we have discussed so far is for two classes. What about multi-class? I mean, the mathematical derivation has been done for two classes. We say that W transpose times X, for example, plus W0 times R, where R can be +1 or -1. For RIT, we say that this should be greater than or equal to 1. So here we have either class 1, okay? So if X belongs to a class CI, then Ri equal to +1. If X belongs to class, does not belong to class CI, then Ri equal to -1. This is simply the multi-class situation. So in multi-class situation, because beginning that we say that C1 or C2. Now we can generalize it. So if you belongs to a class 1, for example, let's say that you have 4 classes, C1, C2, C3, and C4, okay? Now, if your data belongs to C1, then R1 equal to +1. If your data belongs to either class 2 or class 3 or class 4, always Ri or R1 will be -1. So it is called like the right class against the other classes. So this is the simplest way to solve the problem. So if you have like a multi-classes problem, you can apply the same concept of two classes, but you assume all the others in the other class. You don't care where are they, but if they are not belongs to your interested class, then you classify them as -1, regardless in what other class they are. So it is called like one against the others. Okay, and in that case, it is much easier to solve the problem in that case. Of course, you can also solve the problem by modifying the optimization, but it is not that preferred actually. You can solve the problem by modifying the optimization problem, as you can see, that we minimize the distance, minimize the weight actually, or maximize the distance between classes as far as the data belongs to the right class against the other classes. But this will increase the dimension of the problem. So the easiest way to solve is assuming the same concept of two classes. If your data belongs to class of interest C1, for example, or C2, then you take it as R equal to 1 and R equal to -1 for the other classes, and you solve the same problem as we did before. Okay, the last thing for today's lecture is kernel-based regression. The same concept of kernel can be applied also for regression, but actually mainly the support vector machine or the kernel machines mainly applied for classification. The main application is for classification, not for regression. For regression, actually, neural networks and also the other types of regression that we studied in part 2, they can perform in very well. So we don't need to go to this to the kernel-based regression. But however, actually, kernel-based regression it can add some features by using the same concepts of the classification that we have seen. So the idea, I just go through them quite fast. So the idea here is by defining the error in this way. So if the error is within the difference between, here is not a class number, here is the numeric output that we like to be as close as possible. So if the difference between the output and the function that we are building, because this is the function that we try to build, we are optimizing what is the optimum W and W0. Of course, we can also later on extend it for the kernels as well. But if we start with this simple one, so the error is 0 as far as the difference is within certain epsilon. It is like within the margin. So it is called within a tube here. Okay, and the error otherwise is equal to the absolute value of the error minus epsilon. So this is the definition of the error function, and then we minimize, we find the optimum weight which achieve this requirement of the error, which is the requirement of the error that the error is equal to this one. Yeah, so it will be in this shape. And solving this, actually, we can also find the optimum weights which can achieve the regression of the kernel machines for the regression. But as I said, it has some applications, but it is not as important as the classification, the support vector machines for classification. Yeah. So this is actually the function that you can build. It is also based on the support vectors, and this is actually one of the main features why we use the support vectors in order to build a regression as well. When you have a lot of data, when you have like the size of data is extremely large, and building the linear regression with the methods that we have seen in part 2, it can be require highly computation power because of the data is huge. But here, with this concept, we can only build the regression based on the support vectors, only on the support vectors, and this is the main feature of using machine learning or using the kernel machines for the regression. And also you can extend it for the nonlinear by using the same concept of kernels. Yes, that is all for today. About the quiz next Monday. So the quiz will, the topics parts will be only part. It is part 3, no, part 4, part 5, and part 6. Part 7 is not included. So it is part 5, 4, 5, 6, 3 parts included in the written quiz, which will be on Monday. It will be like, I have not decided the time yet, but it is a written quiz, and it included simple problems, but I need to see how you solve it with hand. So it is only 3, maybe it can be 3 problems only, and only 3 parts included. Okay, that's all. Thanks a lot.